Hi, Spring fans. In this lesson, we're going to quickly talk about the motivations behind everything else that we're going to see today. So we have a lot of things that we're going to cover, but let's just take a few minutes, not really focus on code. Let's just talk, okay? I want to kind of lay down the assumptions that motivate what we're trying to do today. Why do we care about reactive programming? And to really appreciate reactive programming, we need to sort of consider what has arrived more recently, what has caused us to sort of take up this question, to take up this challenge now when we could have, and maybe perhaps should have, done so 10 or 15 or 20 years ago. Now keep in mind, reactive programming is not a new solution. It's not a new solution, and the problem that it addresses is a much older problem. It's a very old problem for which you no doubt have, probably already had to provide solutions. It's a problem for which, or with which you've already no doubt tangled. It's something that most of us had to think about, namely, given an application that's in production, how do I handle more users? How do I add more scale to that system? And what I mean by that is, how do I allow more requests to go through? Okay, so again, not a new problem and not a particularly new solution. The problem is old as time, right? It's a very, very old problem. I have more users. I want to handle more users. And the drive for that has become sort of more manifest. The need for that has become more manifest, I would argue, in the last 15 or so odd years. And there's a number of different things to which we can point that sort of lead the way. We can look at the rise of or rather the return of the client service architecture. We can see that since 2007 and the sort of introduction of the Apple iPhone, now most developers have had at least two platforms, at least two client experiences with which to contend. The first of which, of course, is the desktop browser-based application, right? You've got the desktop browser experience for your users. There, a customer can go to your site and click around and drive the creation of new interfaces, right? They can drive the creation of new screens that deliver the data that you need to be able to interact with that service. Well, as soon as we have the iPhone, now we have more than one client. And so it becomes advantageous for organizations to think about how to tease out the services from their user interfaces, right? You don't want a monolithic application anymore because you can't reuse that service functionality, that business logic. It becomes entangled with the thing by which you deliver the user interface. So you tease these things apart. You say, here's the user interface. Perhaps it's a thin client now. We've got Ajax, in 2004, and then we've got sort of so-called smart clients. The average React application or Angular application today vastly out complexifies the average program today, right? If you're a server-side Java engineer, you've no doubt sat there and puzzled through modern day JavaScript because they're just so much more complex than what most of us have to deal with on the server side these days. It turns out it takes a lot more patience to build a user interface than it does to build a massively distributed system on the back end. So these clients are now rich, smart clients on the front end, as delivered through browser-based applications, certainly, but they're also iPhones, they're Androids, they're smart boxes, they're PlayStations, they're Xboxes, they're that one person using Windows Mobile. All these people are driving demand on your service, and that means that you now have to deliver new user experiences. And in order to support that, a lot of organizations move to a service-based architecture or microservices. And in this architecture, suddenly you have more granular HTTP calls. Suddenly, every single user interface that you interact with, that you use to facilitate interactions with your backend service, drives more demand. It drives more requests. If you load a single user interface screen in your average mobile application, that could result, and probably does result, in a cascade of HTTP requests to backend services. Even on the case where you have server-side rendered HTML, such as, for example, with many fast services today, like, for example, Amazon and Twitter. They have isomorphic applications in some cases. These are applications that behave interactively, and through Ajax, they update themselves. They only worry about the delta after they've been loaded. But that first load is actually server-side rendered. So these applications, sometimes, even when you have a server-side rendered user interface, these applications, in turn, make a cascade of calls to other services. So these other services now need to be able to get back a response in time for the load of that single user interface. So it becomes very important to realize that every single user interface could result in a cascade of network calls that you didn't have to deal with before. One user interface could as easily equal one HTTP call or one service call. But now that system is far, far different. So I've just talked about a number of different things here. We've got client service, we've got microservices. These are huge drivers for the need to be able to handle more users, more capacity, right? And perhaps we have the same number of users, but even in that world where we have the same number of users, we have a good deal, many more API calls, right? And that's where we have to address new scale, okay? So now that we've understood the motivations for this new reactive world, let's consider what reactive programming gives us, right? We understand that reactive programming is meant to solve that particular problem. You will no doubt have solved that problem in your own way, in some other way, right? It doesn't have to be reactive programming. So why not just use one of those? And I would say, yeah, you could. I mean, there's some good ones out there that are maybe not great, but they're pragmatic. We have, for example, in the last 10 odd years, seen the industry have a long, healthy discussion around microservices. This idea that I'm going to tease apart my monolithic service architecture, and I'm going to decompose my application into small, singly focused, independently deployable, reusable, bounded contexts, or microservices. Each microservice is a network service, of course. That's how you obtain the autonomy that are so vaunted, so important in the microservice architecture paradigm, first of all. You can move to microservices, and one thing that you do when you move to microservices, in the classic Netflixian sort of sense of the definition of the architecture, is you extract out or eradicate any service state. So sure, you have state, but that service is pushed back to a scalable data tier as best as possible. In the Netflix story, of course, we're told about Cassandra. They used Cassandra to scale out the data architecture. But each service was just a classic stateless HTTP service. Very, very little state. And the benefit of that architecture is that you can then put those stateless services behind a load balancer and scale out horizontally. Any cloud platform today will do that for you pretty quickly, pretty readily. There's a button or a checkbox or something that you can configure in most cloud platforms today that allows you to tease out, or rather to scale out your architecture. You can say, hey, I've got one load balancer, one gateway through which all client requests will flow, but then I want to round robin distribute the load to all these nodes. And so even if any one particular node was unable to scale, you could just add more nodes. Was it the cheapest solution? Probably not. Was it the most efficient? Certainly not. But it worked, and it's cheap enough for a lot of people. So if you're okay with that architecture, and if you're happy just to scale software written in yesteryear that way, then good. You're already in production. That's what matters, right? We care about production. But now that you're there, now that you're in production, and you've made that move, and certainly on the Spring team, we have cared about helping people make that migration from monolithic applications to microservices. Now that you're there, now that you've crossed that particular chasm, I want to have a discussion about how we can do better with our existing nodes. Could we be more efficient? And if so, why not? What are the things that are stopping us from taking our existing software and handling more requests per node? Why do I have to scale that horizontally? Why can't I scale that horizontally and handle more requests per node? And so the question then turns to, well, what's stopping us? Where are we being bottlenecked? And why? There's a lot of different answers for that. It depends on the technology stack in question, certainly. But for the JVM developer today, that answer is very likely going to be threads, right? So suppose you have a typical web server circa 2010, yesteryear. And you have a typical web server parked on port 8080. This is a Java servlet engine of some sort, just a hypothetical. And you've got a very, very simple service there that it takes incoming requests and produces a response. Well, behind the scenes, that code is written in a very simple while loop. While the JavaNet server socket is parked on port 8080 and accepting incoming requests, you block, you wait. And as soon as somebody knocks on that port, basically somebody sends a request to that port, to port 8080 on your service, you spin up a new thread and you produce a response. And in that thread, what are you going to do? Well, you're going to take the incoming input stream coming in from the client, and you're going to take the outgoing output stream that your service is using to produce an output buffer, and you're going to put data in that buffer that gets sent back to the client. What kind of data? Well, could be HTML, could be, JSON and, protocol buffs and all sorts of other things like that. It doesn't really matter, right? What you're doing is you're producing a response that the client can use. How do you produce that response? Well, you're going to talk to a service. You're going to talk to other services. You're going to talk to databases. And so what's happening all the while? The client's connecting to your service and you're connecting to other services. What's happening as you're doing this if you're using Java I/O input streams and output streams? Well, that's where we get into trouble. You see, Java I/O input stream and output stream are blocking abstractions. They're blocking APIs. What that means is when you call inputstream.read in your Java code, you're just going to sit there. You're just going to sit there waiting for the next byte to come. And this is where we get into trouble, because if you look at most services today in the JVM, most of them are out of threads. They can't create more threads, and yet your CPU is very low. It's all but idle, right? Because a lot of the things that we do on a given service today are just I/O interactions. We're just waiting. We're idle. We're parked waiting for bytes to happen. And that means that we're sitting there on those threads, but we're not doing anything with them. We're just in this wait state. That's a really bad place to be, because it means that nobody else can reuse that thread. So what we want to do is find a way to describe our architecture in such a way that we can repurpose existing threads. And the problem that we have, on the JVM at least, is that the APIs that we've traditionally used, namely Java I/O input stream and so on, don't lend themselves particularly well to what we're trying to do. They don't lend themselves to this world of, hey, I want to ask for data and then jump off the thread and then be woken up eventually, asynchronously, when data is available, okay? What we need is to rethink how we describe that world, how we work with data in that way.